As the name suggests, now we are going to see the topic which is direct torque control. Isn't it? Can you see it? Direct torque control. Right. Now, till now we have studied the concept of closed loop control in DC drive. You have seen it. In that, you have seen how a closed loop application in DC drive can be implemented by implementing a speed loop, which can be which can be controlled by a torque loop, and then torque loop will be implemented with the help of armature current loop. Do you remember the last classes? Yes or no?
Yes,
I'll
sir.
just
Yes.
yes, show you. It was like this. In DC machine, or in any machine, I have told you that when you want to implement a closed loop control, then you have to obviously the quantity which you want to control is your speed, but speed loop alone cannot be controlled independently. So to control any speed, you have to implement something which can control the speed. Hope you can see my pad right now. Pad. You can see my writing pad.
Yes, sir.
Okay,
Yes,
love.
sir.
So let's begin. What we have studied in the previous classes. Now, in DC machine, if you remember the block diagram, I'm not all closely control. The speed is compared with reference speed, and this error is processed by any PI controller. It should generate a torque command, but to generate the torque command, we again give it to API controller, which generate a armature current reference, which has to be compared with actual current, and then you can see further on. So this is the closed loop control in DC drive, isn't it? So here also the difference of the speed is controlled by the armature current. In fact, it is controlled by the torque. Now, second case was we have seen field oriented control or vector control. Field oriented control, vector control, again you have done the same thing. Reference speed was compared with actual speed, and the speed error generated was given to some PI controller. It generated IQ star command, isn't it? IQ star was again given to some controller, a PI controller, which generated VQ star. And then you obtain further ABCDQ, right? So in DC machine, it was the armature current to control the torque and field current to control the flux, right? In vector control, it was that IQ component of the current to control the torque and ID component to control the flux. Now the important thing that has to be remembered here is that the important has to be that in all these cases, in whether this vector control important thing is the torque control is indirect. Do you agree with me? Torque control is indirect, isn't it? How? In DC machine, just see in DC machine, the torque control was done with the help of armature current. In field oriented control, again, the torque control was done with the help of electrical current. So that is why these techniques are known as, I can say, indirect control techniques. They are known as indirect control techniques. So industry was looking something which would help to have a control over the torque directly. And therefore this technique came that is known as direct torque control. So I hope now you can understand the meaning of direct torque control. Direct control of torque, isn't it? Now, if we say that it is a direct control of torque, that means kahin na kahin you will have something like this. Your reference speed, we compare with actual speed, it should be fed to some PI controller. It should generate a torque command. It has to be compared with actual torque. Do you agree with me? So this should be the block diagram or any algorithm which is going to have direct control of torque. Now, what should be the advantages and disadvantages of this technique? What should be the advantages and disadvantages of this technique? And the advantages would be, now we have not seen anything, but at least you can say the advantage would be more dynamic because no need of finding some control variable like current, no need of having some control variable like current. Then, as in field oriented control, you have to implement what? ABC to DQ transformation and again back DQ to ABC. So this coordinate transformation requires the rotor angle theta. So this made it very complicated. Your control algorithm was very complicated, right? So direct torque control algorithm, this technique initially was given by a scientist. What was his name? Just I will just let you know. Takahashi. There was a Japanese scientist, Takahashi, in 1980s. He gave this concept of direct torque control. And ABB was the company which initially made the first commercial DTC drive. Okay. Now, this direct torque control technology, since it was a product of ABB, it was a patented product of ABB. So, according to the patent rules, no other companies could make a prototype or a similar drive. So, for 10 to 15 years, just the direct torque control was sole proprietary of ABB. Then afterwards, developed many companies developed the DTC drive. And I have an interesting story to share with you. That's interesting stories regarding me. Crompton Greaves was also in a condition to develop a DTC drive. So I was in touch with their research R&D head, Mr. Samsul Ikram, and we had discussion. Right at that time, I was also doing my PhD, and my topic was direct torque control drive. My research guide were one from Danfoss Electronics, Denmark. So Crompton Greaves offered me. I hope you are listening me.
Yes, sir.
Yes,
So
sir.
Crompton Greaves. I had an interview with the R&D center of Crompton Greaves. At that time, मेरा काम भी complete नहीं हुआ था. मैं काम कर रहा था. So Crompton Greaves, after having an interview with Greaves, they offered a condition that I should come and work at their R&D center. And their condition was that I will develop my PhD work there, the DTC algorithm, direct torque control algorithm. If it gets successfully implemented, then I may get the share in the patent, not फाइनेंशियल शेयर. मतलब जो भी चीज बनेगी वो क्रॉम्पटन ग्रीव्स की कहलाएगी और उससे जो भी पैसा कमाएगी उसमें से मुझे पैसा नहीं मिलने वाला. But I will get the technical share. Okay, this has been developed by some person. But of course, I will get a PhD. So that was a brilliant opportunity for any teacher at that time to be offered by a position by an industry to work in their R&D center. Unfortunately, I should not name the uh, great visionary vice chancellor of that time. I use the word great visionary vice chancellor of that time when my when my PhD supervisor asked him, he personally went to meet him and asked him to please let this boy should work with Crompton Greaves. It will be an asset to your university and it will be helpful for him. So my great visionary vice chancellor, who was a wonderful pseudo researcher, told that it will be a crime if he will send me to the company. And in that way, that story ended very bad. I could not, I could not, the company was ready to take me at the R&D center. My guides were ready, I was ready, but I was not given the permission to join and to work for it. And unfortunately, I was working in my lab. Crompton Greaves were working at that time. दोनों ने अपने अपने लिए काम किया. मेरी इधर PhD हुई, इधर सुना कि Crompton Greaves ने भी अपनी DTC drive बना ली. So this is the way how you see why research dies in our country. If it would have been some other time, in some other place, hopefully the university would have motivated me to get, yes, we should go and join an industry and work with a product which will be very helpful for the student, isn't it? Agreed or not?
Yes, sir.
तो ऐसे महान वाइस चांसलर साहब हुआ करते थे किसी जमाने में, जिनको बहुत ज्ञान था, तो केवल वो दवाओं की बात करते थे. Let's finish that. So let us come to direct torque control algorithm. Right. Now, this is the operating principle of a direct torque control drive. Wait a minute. So can you see this equation number 3.1?
Yes, sir.
Yes, sir.
Now look, I'll just explain you what is the meaning of this. We all know that what is the mathematical equation for, you can say, a flux linkage. What is the mathematical equation for flux linkage? We know that a rate of change of flux linkage is equal to induced EMF, isn't it? The rate of change of flux linkage should be equal to induced EMF, right? So what should be flux linkage? Flux linkage should be the integral of induced EMF. है ना? And what should be induced EMF? Induced EMF should be the applied voltage minus the drop. This is the basic philosophy. Remember, it starts from a very basic simple algorithm, simple philosophy that जो भी आप वोल्टेज इंडक्शन मशीन को दोगे उसमें से अगर स्टेटर के रेजिस्टेंस को ड्रॉप को माइनस कर दिया जाए तो जो आपको मिलेगा वो इंड्यूस्ड ईएमएफ मिलेगा। उस इंड्यूस्ड ईएमएफ का इंटीग्रल करोगे तो आपको क्या मिल जाएगा? फ्लक्स लिंकेज, है ना? नाउ दिस टर्म RSIS अगर इसको नेग्लेक्ट कर दिया जाए so what will happen? You will have, yes, I'll show you. Yes. Yes, just give it. I will share. I want to share you another slide. Now, the same thing as discussed here. Can you see this equation which I have highlighted?
Yes, sir.
Yes, sir.
Yes, sir.
Now you can see. Now I'm going to write this equation in a different way. That is the disk in discrete form. Now, what is the meaning of discrete equation? Can anybody explain what is the meaning of discrete equation?
Sir, which is not continuous.
Yes, because now we all know that this theory which we are going to discuss, this theory will be used to, which has to be implemented on a digital controller. Obviously, आप इस थ्योरी को क्यों डेवलप कर रहे हो? फाइनली आप एक ड्राइव बनाने वाले हो। उस ड्राइव का जो भी एल्गोरिथम बनाओगे वो आप उसको आप किसी कंट्रोलर से इंप्लीमेंट करोगे एक असली मोटर के ऊपर, एंड दैट कंट्रोलर विल बी ऑब्वियसली अ डिजिटल कंट्रोलर, so you will be dealing with digital quantities. So all the algorithms which we are talking right now must be discretized so that the computer or the controller could understand the language which you are going to implement. So starting from this basic equation, now we will see that how we can convert this equation into a discrete equation and then physically interpret the meaning of integration. That is how a controller or a converter, how a digital controller sees an integration operation. Okay. So let us see, convert this equation into a discrete equation. So that was the equation which we have seen right now. Now I'm shifting to my writing pad, fresh page. So a direct torque control drive is based on a simple equation which says that the flux linkage, we know that d by dt of flux linkage is equal to induced EMF to back EMF, which is equal to the voltage minus drop. Okay, IS minus RS. Remember, we are talking about induction motor. अगर आपको याद हो जब आपने बीई में बेसिक इंजीनियरिंग में इंडक्शन मशीन पढ़ी थी, तो व्हाट इज द इंड्यूस्ड ईएमएफ? इंड्यूस्ड ईएमएफ E was equal to root 2 into pi into F into number of turns per phase into winding factor into flux per pole. Yeah, isn't it? So this was the equation. This was an induced EMF, and mathematics says that induced EMF is always the rate of change of flux linkage. So if rate of change of flux linkage is induced EMF, so flux linkage must be integral of induced EMF, isn't it? Right? Very simple, very basic question. And induced EMF is voltage minus R. Remember what is the meaning of these parameters. This is Vs, this equation Vs, then the space vector. Now, what is the space vector? Va, Vb, Vc in natural reference frame. Remember what is natural reference frame? Converted to V alpha beta in 2-axis frame, stationary. And V alpha and V beta could be converted to V at an angle some theta. So this is your space vector. Or you can say that it's like this. Since it stands for voltage, it also stands for current, that is IA, IB, IC converted to I alpha, I beta converted to a state of IC. It is nothing but if you are having three currents IA, IB, IC, they can be equivalently converted to I alpha, I beta in stationary reference frame, which is equivalent to some vector I. So second angle theta. Or you can say that the resultant air gap magnetomotive force F is assumed to be produced by this single space vector IS. समझ में आ गया? Understand?
Yes,
or no?
sir.
Yes. So you have to see that when I am writing now the equation of this type, that flux linkage is the integral of VDT. I am talking in terms of, always remember, now I will be talking in terms of space vector. ये तो आपके दिमाग में क्वेश्चन उठ सकता है ना कि हम तो एक 3 फेज इंडक्शन की बात कर रहे हैं, मोटर की बात कर रहे हैं, तो ये भाई ये वी क्या है, ये क्या वी है, के वी बी है, के वी सी है, और ये तीनों नहीं है तो ये क्या चीज है, लाइन वोल्टेज है, फेज वोल्टेज है. नाउ व्हाट इज द थिंग? Now we are studying a subject which is advanced electric drive, so we will be using some new algorithm. So we are talking about space vectors, right? Okay. Now let us write this equation. D by dt of xi was equal to E, which was approximately equal to V. Right. Now in Laplace domain, isn't it? What is integral? What is the meaning of this operation d by dt? Laplace में क्या होता है?
So multiplication of S.
Very good. That is the thing. अच्छा ये बताओ, मेरी ये जो मैं लिख रहा हूँ स्क्रीन दिख रही है आपको भी?
जी सर.
Yes, sir.
ओके, बड़ी स्लो चल रही है, क्या हो गया इसको? Okay, leave it. So you are right. It is multiplication of S. So S into the state of the state of flux vector lambda S is equal to V. Right. This S is rate of change. In discrete form, इसका मतलब क्या होता है? It is time rate of change of any quantity, isn't it? So this can be written in discrete form as xi s at kth instant minus xi s at k minus 1th instant divided by the small interval of time delta t should be equal to this. Agreed or not? आप किसी भी क्वांटिटी का टाइम रेट ऑफ चेंज निकालना चाहते हैं. टाइम रेट ऑफ चेंज का मतलब क्या होता है? चेंज विथ रिस्पेक्ट टू टाइम, है ना? Isn't it?
Yes, sir.
Yes, sir.
So this xi s of k is a stator flux vector at the kth instant, and xi s of k minus 1 is the stator flux vector at k minus 1 instant. Because you are now going to deal with a digital computer, right? You will be having sensors. You will be converting analog quantities to digital quantities. तो आप जो भी क्वांटिटी मेजर करोगे, आपका एनालॉग से डिजिटल सिग्नल में कन्वर्जन होगा. तो आप एक आपके डिजिटल कंट्रोलर का एक सैम्पलिंग टाइम होगा, आपके सेंसर का एक सैम्पलिंग टाइम होगा, और हर उस माइक्रो सैम्पलिंग इंस्टेंट में वो उस क्वांटिटी की वैल्यू को लेगा, उसको डिस्क्रिटाइज करेगा, डिजिटल में आएगा और उसको कंप्यूटर को देता जाएगा, है ना? In this way, that computer will work. So everything will be in the form of discrete equation. So the time rate of change of flux linkage can be written as in this way. Right. Now let us see this. So we know that time rate of change of flux linkage is equal to applied voltage B. So it can be elaborated as xi s of k minus xi s of k minus 1 for the small time interval d is equal to the vector at kth instant, isn't it? So what is xi s of k? It is equal to the vector at kth instant multiplied by delta t plus xi s at k minus 1th instant. Agreed? Isn't it?
Yes, sir.
So this equation says that the flux linkage at kth instant should be equal to flux linkage at k minus 1th instant plus something. So if this is flux linkage, this should also be a parameter that should be what? A flux linkage, isn't it? होना चाहिए कि नहीं होना चाहिए? This is a vector equation. Vector sum, ये एक vector addition है. Because this flux vector, this is space vector voltage, these are all vector quantities which are rotating in phase and they are represented as space vectors. So flux linkage at kth instant is equal to flux linkage at k minus 1th instant plus this plus something is nothing but the change in flux linkage, isn't it? Change हुआ ना? I can only shift here to here. इस equation को ऐसे लिख सकता था ना? Xi s of k minus xi s of k minus 1 is equal to Vs of k into delta t. ये भी हो सकता था ना? Understood? So what is this? ये क्या चीज है? It is representing what? ये क्या represent करता है? A change in what? Stator flux linkage. Yes? Understood?
Yes, sir.
Now let us come to our main philosophy. Let us say this is the stationary DQ reference frame of the stator. अब हम इस चैप्टर को इसलिए पढ़ रहे हैं ताकि हम इस कोऑर्डिनेट ट्रांसफॉर्मेशन का फिजिकल इंटरप्रिटेशन निकाल सकें, and we are able to understand the practical use of this coordinate transformation, isn't it? And I have started this chapter with the basic. I told you that there are many reference frame theories. One is natural reference frames, stationary reference frame, rotating reference frame. So now we are going to see everything in a axis stationary reference frame. मतलब हम जो भी अब देखेंगे, we are going to be dealing with the variables which are being transformed into a 2S stationary reference frame aligned to the stator. Each and every word has an important meaning. So याद रखना, हर शब्द का एक महत्व है. Last class में जो हमने पढ़ा था, the thing which you have studied in the last class, which was field-oriented control, है ना? Remember field-oriented control? So in field-oriented control, you all know that the entire algorithm of FOC was based on conversion of IA, IB, IC, written in short form of IABC, to be transformed to IDQ, where this transformation was done on a rotating reference frame. A rotating reference frame aligned to the rotor. Now in direct torque control, DTC, we are going to have a transformation from the natural reference frame to I alpha beta, or VABC to V alpha beta, or alpha ABC to alpha, then lambda ABC to lambda alpha beta. Now, just from common sense, which is less complex, this one or this one? Which algorithm do you feel should be less complex? FOC or DTC, or simply working in rotating reference frame or working in a stationary reference frame? Here your reference frame is alpha beta, sorry, DQ. And here reference frame is alpha beta. This is rotating, this is stationary. Which will be more easier, less complex?
That is stationary.
Yes, very good. Because a transformation from ABC to alpha beta will only involve some angle theta which are constant. But here a transformation requires an angle theta which is a function of your speed, integral of omega dt. है ना? You have to sense the rotor position every time. कोई घूमती हुई एक्सिस के अक्रॉस अगर कंपोनेंट्स निकालना हो, so you have to continuously know the position of that reference frame. So rotor position has to be selected at every instant, has to be known. Here you don't have to know rotor position. So the first advantage of DTC is it is less complex compared to FOC. Why? Because it operates in stationary reference frame. This operates in rotating reference frame. So I hope with these two applications, though we have not finished DTC, you have understood the physical interpretation of reference frame. अब समझ में आ गया कि ये जो हमें पूरी reference frame theory पढ़ाई गई थी, इसका उद्देश्य क्या है? Isn't it? I hope you got the point. Now I hope you can see the applications of reference frame theory. The different reference frames transformations are used by different people for different applications. So some people found that if we can operate in a stationary reference frame, then your life becomes easier. But let us see how you can operate in a stationary reference frame and get the same dynamic performance as that of a DC drive. Because from our philosophy, we have learned that if you want to get a performance similar to a DC drive, you must have a component of the stator which should have an equivalent parameters as DC drive, that is ID and IQ, है ना? ये मैंने बताया था ना आपको कि जब हम ट्रांसफॉर्मेशन करते हैं रोटेटिंग रेफरेंस फ्रेम में, तो जो आपके वेरिएबल्स है वे दे गेट कन्वर्ट फ्रॉम स्टेट फ्रॉम time varying quantities to DC quantities. ID and IQ are like DC quantities, and ID and IQ behave similarly as armature current and field current in a DC machine. So in the next class, with this philosophy in mind, we will start DTC drive. Remember, अभी भी मैं आपसे बोल रहा हूँ, ये जो डायरेक्ट टॉर्क कंट्रोल एल्गोरिथम है, अभी भी इसके ऊपर ये बुक्स में अभी नहीं आया इतना ज़्यादा. You will see research papers. Although this technology is not new, in the 90s it was developed, and now commercial products are being made. but still it is not in books. So whatever I am teaching, you may note down. I will share the slides. You will get material, but you will normally get the material from some PhD thesis or a master's thesis. Okay. So I'm just stopping my presentation, downloading the attendance. अभी मैं उस पे जा रहा हूँ, रोल प्लेटफॉर्म पे, ठीक है? You can mark your attendance right now. सुन लिया?
Yes,
जी
sir.
सर.
Yes, sir.
So now we are finishing the class, and the next class we will see this director control algorithm in detail. Thank you.
Thank you, sir.